Welcome back. In this video, I'll be discussing normally distributed random variables. So a continuous random variable, I'm just going to say RV for random variable, is normally distributed if its relative frequency histogram, has the shape of a normal curve. In other words, it has a bell shape. That's what we commonly call that. All right, so basically we were looking for something like, like this. Okay. All right, so what are properties of this normal distribution and uh, let's see, characteristic properties that we should know about any random variable that's normally distributed. One thing that I have you notice is that this is a symmetric distribution. So notice if I drew a little dashed line, down the middle of this bell-shaped curve, if I were drawing this perfectly, it would fold over on top of itself. It's the mirror image of itself left to right, and it's symmetric, and that line of symmetry is at the mean. So we say it's symmetric about the mean, mu. So that's the Greek letter mu. It's the symbol we use for a population mean. Something else to notice. The mean, so that's value here, is equal to the median and also the mode. So there is a single peak in this distribution that's right here. And so the mean equals the median equals the mode. And just a little reminder, the median tells us that half of the values are to the left and the other half of our values are to the right. And the median tells us that the values near this peak are the most common. That's the highest point. So the height of this curve, where it's higher, values are more likely. All right, let's see. This curve has inflection points at the mean minus 1 standard deviation and the mean plus a standard deviation. So remember, an inflection point is where the curve changes from being curved up to down. So there are two such places. So there's an inflection point, right here and right here. And if we look at those are at the mean plus a standard deviation and the mean minus a standard deviation. And that's the mean right in the middle. Now, I'm going to mark those again on this main picture up here. Once we know the length of a standard deviation, so that's from here to here, I can mark off other standard deviations by just marking off that same distance. So this would be the mean plus 1, and the mean plus 2, and the mean plus 3 standard deviations. And of course that works going the other side. This would be the mean minus a standard deviation, minus 2, and minus 3. Okay, what else should we know? Oh, this is a continuous random variable. We use the area under the curve to represent probability. So the total area under this normal curve, total area under the curve is 1. And let's see, the area to the left, or if you wanted to say to the right, it'd be the true either way. The area to the left or right is 0.5. And I kind of said that here where we refer to that as the median. I said half of the probability or area is to the left and half is to the right. Let's see. I'll also mention that as x increases, so these are the values along this real number line. As x increases, without bound, if there's no restrictions on the values here, the graph approaches but never reaches the horizontal axis. So, this is a number line that goes on and on and on and on. And what we're saying is that this gets close, as we go towards infinity, that gets closer and closer and closer. But it never actually touches, or certainly doesn't go below that horizontal axis. Another thing I'd like to add, well, a couple things. Firstly, a reminder about the empirical rule. This is also sometimes referred to as the 68, 95, 99.7 rule. And what that says is if we look at our normal distribution and mark off 1, 2, and 3 standard deviations in either direction, that we have 68% of our data between within 1 standard deviation, 95% within 2, and 99.7 within 3. Now, in terms of a random variable and area, so the area under the curve and above the interval mu minus 1 sigma, mu plus 1 sigma. So that's an interval there. Area under the curve and above this interval is 0.68. So, and I can say the area, that's under the curve and above this interval from, mu plus or minus 2 standard deviations, that area is 0.95, and mu plus or minus 3 sigma, that area would be 0.997. So I'm basically just restating the empirical rule in terms of area under the curve, because with these continuous random variables, we are equating area under the curve with the probability. Okay, so lastly for this video, I want to just say that any normally distributed random variable and again, I want to just use RV for random variable, is completely defined by the parameters mu, and that gives us tells us where the center is of the distribution, center of distribution, and sigma, which tells us about the spread of the distribution. So let me just get some paper to put underneath here, and I'm going to mark off a number line, and let's put some markers on here. I'm going to say that this is 100, this is 110, 120, 130, 140, 150, 160 right here, 170, and so forth. And this would be 90, 80, 70, 60, 50, 40, 30. All right, so first I'm going to draw a curve which is going to be centered. Let's do this one centered at 60. And let's say that it has a standard deviation of 10. Yeah. Okay. All right, so to draw this, I'm going to try to make my, all right. The center here, mu, is at 60. Now I drew that such that my inflection points were about here and here. So notice that the inflection points, that has a from here to here, that distance is from 50 to 60, so that has 10 units, and same thing from here to here. So sigma is 10. All right. Now let's say I have another normal distribution, and this one's going to be centered at 100. And for this one, though, I'm going to have a standard deviation of 30. So I'm going to try to get up to here, 30. And I'm going to have a curve that goes like this. Now, the area that's under this curve, the green one, if I did this, really well, that has an area of 1, and that should be the same area as under this. The point is that if both these have the same area underneath of it, so the same amount of space, then then notice what happens when I change the mean from 60 to 100. All that does is shift the center of the curve from here over to here. But as far as changing the shape of the curve, it's the standard deviation. So when I move the standard deviation out and say that it's 30 as opposed to 10, if I end up with this kind of a short and squat, like a flattened curve, as opposed to this that is a little bit steeper. And if I wanted to do even another example, maybe we'll have one centered at 130, and maybe this one will just have an inflection point at 5. So maybe it will look like this. Now, again, this should have the same area underneath it as the other two. This one has a mean of 130, and that inflection point, I meant to draw it so that it was about here at 135, so that would have a standard deviation of just 5. So the point that I want to make is, when I say that a normally distributed random variable is completely defined by the parameters mu and sigma, this guy tells us where the center is on the number line, and this tells us about the spread. So whether things are kind of compressed and tight around the mean, or as in the case of this green one, where there's things are more spread out about the mean, and then the red one here is sort of in the middle. Okay, so with that in mind, let's look at an example, uh, an application of the normal distribution. And let's say that you know that the lives of refrigerators, we'll say, are normally distributed. And the average life for a refrigerator is 14 years. But not every refrigerator lasts exactly 14 years. There's some variety. And so the standard deviation for the mean is 2.5 years. Now, even though I've said that these values determine the shape, usually when I'm drawing a normal curve, I draw them all pretty much the same way, unless I'm trying to illustrate the differences and make a comparison. So I'm going to draw my standard bell shape with 14 in the center. I draw my 3 lines to the right and 3 lines to the left to represent 1, 2, and 3 standard deviations. So this would be 16.5, this would be 19, and 21.5, and this would be 11.5, and 9, and 6.5. So there is the curve that represents this distribution. And so suppose we want to shade the region that represents the proportion that lasts, let's say, 19 years. So that would be from here over. Then let's see, what if we wanted to find this area and interpret that. So I would just recall that from here to here, that total is my 95%, or the area would be 0.95. Now, if I just take half of that, so from here to here, that area would be half of 0.95, which would be 0.475. Now, I'm going to use a fact from earlier where I said, that, from here over is 0.5. So from here all the way over is 0.5. But I'm really just interested in this piece over. So if I take my total, which is 0.5, and subtract, so 0.500 minus 0.475, I'll get 0.025. That must be this area, 0.025. Now, what does that mean in terms of the context here of this problem? So there are two ways that you can interpret this. You could say that 0.25 or 2.5%. That would be if I'm moving this over 2.5% of refrigerators last at least 19 years. So that'd be 19 or more. Another way to interpret this would be to say if you select a refrige at random, there is a 2.5% chance it will last at least 19 years. So those are two options. Before I leave, one more thing here to say about this. As far as the notation that we'll use. So knowing that mu and sigma completely define this, the shorthand here would be to say x is, so remember the tilde says that this random variable follows a certain distribution. We can just use a capital N for normal, and then we'll put mu and sigma in parentheses. Those are the two parameters. So in this example with refrigerators, I could say that x, which represents the life of refrigerators, is normally distributed with mean 14 and standard deviation 2.5. We'll always put them in that order, mean followed by standard deviation. All right, I hope that helps with your understanding of normally distributed random variables.